Hi everyone, I'm super excited to talk to you today and I hope you've all had a fantastic conference so far. My name is Jo Franchetti and I'm a developer advocate at Ably, which means that I get to make all kinds of fun projects to show off what Ably can do. Ably is a platform that provides a reliable and pleasant to use real-time messaging infrastructure that allows developers like you to build apps that use real-time data. And I make all kinds of fun things like this web app that shows where all of the buses in Connecticut are live on a map as they move around. Or this peer-to-peer web-based multiplayer game. And one of my favorite things to make is wearable technology, specifically things with lots of lights on, because I like to be sparkly. And I started to make wearable tech projects a couple of years ago, my first being a light-up, tweet-controlled wedding dress. And when I started, I had no real clue about what I was doing, and I made a few very silly mistakes. Mistakes around choices of hardware, how to connect the hardware together. And my hope for this talk is to give you a little direction for those of you who are looking to get into hardware projects, to help you get over that initial hurdle of hardware is scary. So with this project, I wanted to make something that we could all interact with together, because I don't know about you, but with all the social distancing and the lockdown, I've been missing having friends and colleagues and going to conferences in person and just having humans around me. And so I thought, what if I made a wearable that lets my friends change the color of my clothing while I'm wearing it in real time? I'd be able to see the changes they were making as they happened, kind of like a wearable multiplayer version of Microsoft Paint. So in order to realize this dream, we're going to need a few things. Firstly, we're going to need an array of lights which can change color. Secondly, we're going to need a microprocessor to control these lights. We're going to need an app where users can set their colors. And we're going to need a method of sending messages to and from the app and the microprocessor. So let's start with the array of lights. It's going to be a 16 by 16 grid of LEDs. And the LEDs that we'll be using in this project are called addressible RGB LEDs. Addressable means that we can target each one, and RGB means that we can set it to basically any color we can think of, using a similar color value to what I'm sure you've already seen in CSS. Your RGB values with the brackets and 3 numbers. Incidentally, the product name of these pixels is NeoPixels if you're looking to buy them online. The LEDs come in these ribbon strips, which makes working with them nice and easy, as we don't have to individually solder each LED. The strips are also great because not having those individual solder points means that you have fewer points of weakness. It can flex a lot easier without worry of snapping at a solder point. And the strips have nice clear labeling to show which lines are carrying the data, which are carrying the ground, and which are carrying the power. So you're much less likely to make a mistake when you're connecting them up together. And to keep the strips safe in the wearable, I sewed 2 pieces of fabric together to make a pocket to insert each strip into, visualized here. So imagine sewing along each line over 2 pieces of fabric. The actuality of my sewing is shown here in the photograph. I'm not great at sewing, but it did the trick. And once the strips are inserted into each pocket, they then need to be soldered together so that the power, data, and ground lines are all connected up together. And you can buy a soldering iron and solder from around £30 online. And you can see here that I used what is called single core copper wire to connect them all together. And I recommend also getting a heat-proof silicone mat to protect your desk. And incidentally, these double up as excellent baking sheets for cookies. And there are a lot of tutorial videos on soldering online, so I'm not going to go into it here. Suffice to say that it isn't too scary, and once you get the hang of it and you've had a few goes at practicing, you'll find it very easy. So, once both ends are soldered, we have a finished, flexible LED array, which looks like this. So you can hopefully see here that the array is quite flexible. I can bend it, which is important for a wearable. So now we have an array of LEDs, we need a way to actually control what colours are sent to it. And a microprocessor is useful here because they can do enough calculations to control the lights, but they're nice and small so they can be easily hidden within a wearable. And I opted for this microprocessor, which is called the Adafruit Feather Huzzah. I like this one because it's super small. It measures 5 centimeters by 2 centimeters, and it comes with Wi-Fi on the board already, which means that I can easily connect it to the internet. And it doesn't cost too much. It's around £20 to buy. And the great thing about small microprocessors like this is that they're very low power. They can take power from a USB battery or from a USB cable plugged into your laptop. And they run C and C++ code out of the box. You write software with them using the Arduino IDE, and the Arduino IDE is great because it comes with all the libraries that you're going to need. It's got a bunch of sample code that you can see so you can get set up and running with the board very quickly. And the code for the Huzzah looks like this. So what you can see here on the top line, I have included the library for the NeoPixels that I'm going to need. And then I have defined the pin that I'm going to use. So this is pin number 4 here. That's the pin on the board that the data is going to be sent out on. Then I have set up the number of lights in the array, which is 16 by 16, so 256 lights in total. Then I've told it what kind of lights I am using. So I am using these Neo RGB lights. And this is an important thing to double check which kind of lights you are using. They might be Neo RGB or they might be Neo RGBW, which will require you to send an extra white value, which is the brightness value, when you're sending your color to the board. Then we are setting up the strip and initializing it, which sets all the LEDs to an off state with strip.begin. And then we're going to loop through each LED, so from 0 to the total number of lights, and we are going to set the pixel color to be 255, 255, 255, which hopefully you can recognize is white. And if we have a look at the board itself, so here's the board, this is pin 4. Just here you can see the 4 label. Then we have power going into the USB port, and then we have ground going to ground. And the board can very easily be connected to a USB battery through this USB micro port just here. So now we have a display and we have a way of controlling it with the microcontroller. Now we need a way to tell the controller what colors to set. And being a developer, I opted for a web app, of course. And you can check out the code for the web app at the link that I've put here. But don't worry, I will also share the slides at the end of the talk so you can peruse the code at your leisure. The app looks like this. It's got some buttons at the top where the user can pick a color, and it has an SVG of squares that represents the pixels in the array. And each square in the SVG has an ID with its number in the array, 0, 1, 2, 3, 4, etc., etc. And once a color and a square has been selected by the user, the app updates the fill color of that square to match the selected color. But we also want it to light up the correct LED on the t-shirt, which means that I need some way of getting data from the app to the t-shirt. And we can do that with a real-time messaging service. We would use this to send messages containing the color and the pixel number from the app to the t-shirt. And in this case, I'm going to use Ably to do this. It allows me to create a channel and to publish messages to that channel from the app as they happen. The microcontroller on the t-shirt can then subscribe to this channel and get these messages instantly. We can also subscribe all the other users of the app to the channel as well, and they'll listen for changes so that their displays will change as other users make changes as well. And every time a pixel is changed, a message is published to the channel and all of the subscribers will receive it. And you can have a go of the app if you go to ably-mqtt-io-tshirt.glitch.me. So let's take a look at some of the code for the app. The app is built with Node and Express, and on the front end I used Ably's messaging platform to set me up with a channel. Then I used their JavaScript SDK to manage the publishing and subscribing to messages on this channel. So here what we're doing is we are creating a new instance of Ably, and then we are creating and connecting to a channel called tshirt. And as I mentioned earlier, the cool thing about PubSub is that all of the users of this web app are also going to be subscribed to these messages. So their clients will update as other people paint with them. And we're using the Ably's, the SDK comes with a create token request feature, which allows us to easily authenticate. And on the back end, our Node server is going to require the Ably Promises SDK to do all of our authentication for us and to create the Ably token requests that we need. And the nice thing about using tokens instead of setting the API key directly means that you keep your API key safe from misuse. So now that we've established a connection to a channel, we need to publish a message to that channel when somebody clicks on a square. So what we're going to do is we will add a listener for a click on each pixel square. And when clicked, what it will do is it will get the number of the square. It'll change the fill of the square, which is SVG language for background color, basically. And then it will publish both the square number and the color value which was selected onto our t-shirt channel. So let's imagine we have a message sent that looks like this. So the name of the message is going to be t-shirt and the data that is sent is 001-AA00FF. So what we're saying here is that the user has clicked pixel number 1 and they've set it to the color purple. And that hash is actually a useful place where we can cut this message in half and get the two separate values. So we want the web app to display the pixels as well as the t-shirt to display the pixels. So we're going to subscribe to that channel as well as publish to it to get the updated pixel values, along with an optional reset that I'm setting here, just in case anybody manages to draw something not safe for work on a 16 by 16 pixel array. And what happens here is the sync pixel value will split up the square number and the color value, and it will apply the supplied fill color to the relevant square in the t-shirt. The reset value is what will set all of the squares to blank if I press my secret reset button. So now our app can update its own colors and the colors of any other users, and it can also send data to the Feather Huzzah. You're probably familiar with HTTP, which is the protocol that browsers use to request web pages. And HTTP is a protocol, the Hypertext Transfer Protocol. And protocol just means it's the way that two things talk to each other. And HTTP is great. It powers websites and APIs, and it's built to be descriptive and flexible. And it can be used for IoT connections, but it's not lightweight, and it's not terribly fast. And another problem with HTTP is that it's pull only. The device has to constantly connect and ask, are there any updates? How about now? Have we had any updates now? Which is really data and time consuming. And on low power devices, such as the board that we're using here, we don't have very much memory, we don't have very much power, and we potentially don't have very much bandwidth. So we need to use protocols that are designed to be small and fast. And that is where MQTT comes in, which is a connectivity protocol which was designed to be extremely lightweight. It is the message queuing telemetry transport protocol. And connecting to a server with this takes only about 80 bytes. And the brilliant thing is that the device stays connected the entire time. Data is published when it's pushed from the device to the server, and the device subscribes to data which is pushed down from the server. And because the size of the data that is sent over MQTT is very small by design, messages can be sent really quickly, which makes the hardware very responsive, making it feasible to change the lights on the t-shirt in real time as they're being changed in the app. And in order to use MQTT, you will need an MQTT broker. And a broker is just a server that devices connect to using the MQTT protocol in order to listen for messages. It will keep track of all the clients that are connected and the topics that they are subscribed to, and will forward any messages from anybody to any other subscribers. And in this case, I'm using Ably's MQTT broker, mqtt.ably.io, as my broker. The awesome thing about Ably is that any messages that we send with the JavaScript SDK are sent out over MQTT via the Ably MQTT broker for free. We don't have to do any extra setup. It's automatic, which seems like a winner to me. So let's talk about how we connect the microcontroller to the MQTT broker. So we're going to use the Adafruit Feather Huzzah with the Arduino IDE. And the setup is actually really nice and straightforward. You can install the IDE, and there's a really clear walkthrough on how to set it up, which is provided by Adafruit on their website, and I put the link in the slide there. The IDE also comes with a whole bunch of example code for beginners, and it also comes with all the libraries that you're going to need for this project. So in order to connect the board to Wi-Fi, you're going to need the Wi-Fi client secure library, which you can see I've included in this code snippet. And you're also going to need the MQTT library in order to connect to MQTT. Then what I've done here is I've created a config object to make setting up these connections a bit simpler. So in this config, I have got my Wi-Fi credentials, so my SSID name and password. Then I've got the URL of the broker that I'm using and the port that it's going to connect to, and my username and password, which are the two halves of your Ably API key. Then this scary looking blob of text that we've got down here is what is called the fingerprint or the thumbprint, depending on which browser you're using, of the SSL certificate from https://mqtt.ably.io. So you are going to need to get this in order for your Wi-Fi client secure library to connect. If you don't provide this fingerprint, the connection will fail. And the final thing that we're doing is setting up which channel the board needs to subscribe to, this t-shirt channel. So, similar to what we did for the web app, we need the Feather Huzzah to connect to the Ably MQTT server and then subscribe to the channel. First, we create new instances of the Wi-Fi client secure and the MQTT client. And while we're connected to the Wi-Fi, the secure client lets MQTT use SSL to connect to our Ably channel using the credentials from the config, which is what we're doing just here. So we are connecting, we are setting the user and the password credentials from the config, we are telling the serial to print connected. So if we are connected via USB to our computer, we can open up our serial monitor and double check that the client has connected. Then we are setting it to subscribe to the channel that we set up. And if it doesn't manage to subscribe or to connect, it'll say that it failed to connect to MQTT on our serial monitor. When a message is received, we can process it. So let's say we had the message that we looked at earlier. So this one that has the name of t-shirt, data of 1, and a color of purple. We're going to split up that hash character into two separate strings. Then we're going to convert the hex into RGB. Then we're going to send the pixel number and the RGB values to the lights to update. Now, the eagle-eyed amongst you may have spotted a bit of a mistake that I made when I was wiring up the lights. So let's take another look at that array of squares from the web app. So I gave each of the pixels a number to represent the number of pixels in my LED array, like this. So it goes from left to right, because that is how we read, and that is how arrays work. But this isn't how I soldered my lights together. I wanted to keep my wires nice and neat, so I soldered these little jumps at either end, so that I didn't have long trailing wires taking one end of the ribbon back to the front of the other end. But if I was to represent this as LEDs with our pixel numbers, my array actually now looks like this, which I have affectionately termed snake mode. That is my new method of enumeration. It starts on the right and it snakes all the way down the board. Which means that what I have to essentially do is reverse every other line of the array, which was a bit of a mistake. So what I did on the board is I made a method which checks whether the position needs to be reversed. So here I have X and Y values to work out where the pixel should actually go, X and Y. And to calculate which row the pixel is on, we divide the pixel number by 16 and then modulo 2 to work out whether we're on an even or an odd row. Then we can work out how many pixels came in all of the rows before that pixel. And if it's an odd row, we minus the X position from 15 to get its flipped position. And if it's not, we just take the position as it is. Then we add on the number of pixels that came before it, and this is how we calculate the new position in snake mode. And I'm told that this is actually how some pixel arrays work, due to the exact reasons that I made it this way. So we have fewer trailing wires. So now I have an app which can send a message. I have a board which can receive it and process it. And I have a LED array that can receive those colors. So now it's time for some demos. And you might have seen the t-shirt lighting up behind me because I tweeted out earlier and asked people to have a play with it. But now I'm going to. So let's try this out. Let's draw something. Maybe a little heart over here. And you should be able to see it turn up on my t-shirt. Someone has very sweetly written Joe on here. And I know those of you who are watching this won't be watching it live, but you can still all interact with the app and you'll be able to see each other's colors as you choose them, but they won't obviously display on the t-shirt, sadly. So we say thank you to the demo gods for blessing us today. This seems to have all gone very smoothly. And thank you all for listening to my talk. If you want to check out the project, all of the code is on GitHub at this link right here, github.com/thisisjoefrank/interactive-lights. And there's the code for the app along with the code for the board itself, which I haven't actually shown, but you can see it just here. This is the board that is powering the lights. And the battery that I'm using to power the t-shirt, actually, this is it here. So it's nice and small, easy to fit into a pocket. If you would like to ask me any questions about this project, you can find me at thisisjoefrank on Twitter or at Ably Realtime. And I would really love to see any projects that you make with this. The code is all open source, so please take it and turn it into whatever you like. And again, thank you so much for listening. I have been Jo Franchetti. I hope you have a fabulous rest of conference.